Hey, good morning, my dear students. This is Dr. Shivam Mishra, and currently I'm working as an associate professor in Department of Mechanical Engineering, GL Bajaj Institute of Technology and Management, Greater Noida. Today again I'm here with a video that has multi-stage vapor compression refrigeration system, which includes intercooling as well as the combination of intercooling and flash gas removal. For the flash gas removal, we have already studied in the previous lecture. Here we will study about the intercooling and the combination of the both. So today I am going to discuss multi-stage vapor compression refrigeration system with intercooling as well as the combination of flash gas removal. This is for the subject refrigeration and air conditioning for the third year students, and the subject code for the same is RME 061. In the previous lectures I have discussed about the flash gas removal. Today I am going to discuss the intercooling in multi-stage compression system. As all I have already told you that these two concepts are the one of the most integral part before we going to study the multi-stage vapor compression system. Also, we know that the compressor is an open system, and work done for the same can be given as integral 1 to 2, which is the from state 1 to state 2 minus VdP, and the same can further be reduced to n divided by n minus 1 P1 V1 in bracket 1 minus P2 by P1 to the power n minus 1 by n, where P1 and P2 are the inlet and the exit states of the pressures, while the specific volume V1 is the specific volume of the refrigerant at the entry to the compressor, and N is the polytropic index. From the above equation, it is clearly observed that work input to the compressor is directly proportional to the specific volume of the refrigerant which is entering the compressor. So, if we will be able to reduce the specific volume at the entry to the compressor, we will always have a reduction of compressor work input. So for doing the same, we will have to reduce the temperature in that is how we can reduce the specific volume of the refrigerant. So this is the idea behind the intercooling. To better understand the concept of intercooling in multi-stage vapor compression refrigeration system, we will discuss it with two curves, that is pressure versus volume curve as well as the pressure versus specific enthalpy curve. So on my left side it is pressure versus volume curve. Here we can clearly see the points, that is 1, 2, 2 dash, 4 and 3. So one by one we will proceed. Point 1 to 2 dash, if I will go from point 1 to directly to point 2 dash, it shows the compression in a single stage compressor of the refrigerant, while 1 to 2 is the compression of the refrigerant vapor in a single stage compression. 2 to 3 is shows the intercooling part, where the heat rejection takes place either by exchanging heat with the water cooled heat exchanger or by the flash gas removal. 3 to 4 is again the compression in the second stage of compressor of the remaining refrigerant. Okay, so the area 2, 2 dash 4 and 3 clearly shows that there is reduction in the specific work, because as I already told you in the previous slide that if we will be able to reduce the specific volume at the entry to the compressor, we will always observe a reduction in the specific work of the compressor. So here we can see the specific volume at point 4 is very less in comparison to the specific volume at point 2 dash. So by doing the intercooling part, we have saved that much amount of work to the compressor. Similar thing can also be observed in pH curve, pressure versus enthalpy curve, that point 1 to 2 dash directly shows the compression in a single stage compressor, while 1 to 2, then 2 to 3 and 3 to 4 shows the compression of the refrigerant in a single stage compression, followed by the intercooling, and then again it is followed by the second stage of compression. Here we can also see that the point 2, 2 dash, 4 and 3 clearly shows the reduction of specific work. Similar thing has also been written in the theoretical form in the below slide. We can observe that from the pH curve that if H4 minus H3, if I will have a enthalpy difference point between point 0.3 and point 0.4, it always shows that it is always lesser in comparison to the specific enthalpy difference between H2 dash and H2. So here we can see that intercooling may be achieved by two processes. First one is water cooled heat exchanger or by refrigerant in a flash tank. The water cooled intercooling is not always possible because it depends on the availability of the cold water of desired temperature where the heat rejection is to be takes place with the uh, superheated vapor. Now, water cooling is commonly used for the air compressors only. Intercooling not only reduces the work input but also the compressor discharge temperature is further reduced. So, it leads to the better life and the lubrication of the compressor. In the present slide, we can see the combination of intercooling with liquid refrigerant in the flash tank. On the left hand side, there is the schematic diagram which represents a low stage compressor, a high stage compressor, a flash tank which is at an intermediate pressure PI, and a flash tank intercooler. The process is as follows. The vapor refrigerant at point 1 is compressed in the low stage compressor, and it reaches the state 2. The state 2 is of superheated vapor state. Now, since the temperature of superheated vapor is very much high, now when it goes to the flash tank, because of the heat removal, the liquid refrigerant is converted into the vapor refrigerant, and some extra amount of vapor is supplied to the high stage of compressor, which is represented by the state 3. The state 4 is after the high stage compression. The point 6 represents the liquid refrigerant which is coming from the condenser, which is again fed to the flash tank where the separation of liquid as well as the vapor refrigerant takes place. After the separation, the liquid refrigerant is again fed to the throttling valve where the expansion takes place, and then it is supplied to the evaporator. Here we can see on the right hand side 1 to 2 is the saturated refrigerant which is compressed in low stage compressor, the liquid refrigerant in the superheated state, and it is desuperheated within the flash tank where the vapor bubbles are formed. Due to the heat rejection, the flash tank, some extra amount of vapor will also be there. This is the reason that mass of vapor at state 1 is less in comparison to the mass of vapor dealt by the stage 2 of compressor. So we cannot say that the liquid refrigerant intercooling saves the compressor work input because of the extra amount of vapor dealt by the stage 2 compressor. The slide shows the intercooling with external water-cooled heat exchanger. The schematic diagram of the same is represented on the left-hand side, which shows a low-stage compressor, a heat exchanger, which is a counterflow heat exchanger, and a high-stage compressor. The state 1 is the vapor state of the refrigerant, which enters the low-stage compressor, compressed up to a desired pressure level as per the design of the compressor, which reaches to state 2, and state 2 is of a superheated state, which is again supplied to a water cooled heat exchanger where the cold water comes in and which exchanges heat with the superheated vapor, and the hot water goes out. After this, the temperature of state 2, the temperature of the refrigerant vapor is reduces in comparison to the temperature of the state 2, which may be uh, saturated vapor or a few degrees lower to the temperature of the superheated vapor at state 2, and then it is again fed to the high stage compressor process. So the process is like the temperature of the cold water is lesser than the superheated vapor. That is the reason, because temperature of the water is very less in comparison to the temperature of superheated vapor at state 2. So cooling is done in the heat exchanger by the heat exchanger, which is a counterflow heat exchanger. After this, the temperature of the vapor after going through the heat exchanger reduces up to some extent. That is, T3 is less in comparison to T2. The water intercooling has a problem that it cannot always be preferred at each and every location because of the lack of availability of the cold water. Again, the total power input to the system decreases or not depends on whether the increased power consumption is due to high mass flow rate is compensated by the reduction of specific work of compression or not. If it is an ammonia refrigerant, the power consumption reduces with liquid intercooling, while if it is refrigerant R12 and R22, the power consumption is increased, and hence the liquid intercooling cannot be preferred for R12 and R22. The present slide shows the two-stage compression system with flash gas removal and intercooling. There is a combination of schematic arrangement as well as the pH chart of the same. Firstly, we will discuss about the schematic arrangement, which includes compressor 1, a water intercooler, a flash tank, a compressor 2, a condenser, and an evaporator. First, it will be better to understand this schematic arrangement by the pH chart, where we can represent it as well. The vapor at state 1 is fed to compressor 1, where it gets compressed to state 2. The state 2 is of very high temperature, which is obviously a superheated vapor state. 2 to 3, the water intercooler is there, where the heat exchange takes place. It is a counterflow heat exchanger. 3 to 4 shows 3 to 4 shows the extra amount of heat exchange which is takes place in a flash tank because of the heat exchange between the superheated vapor as well as the liquid refrigerant. This point 4 is now fed to the compressor 2, where it gets compressed to state 5. Then again 5 to 6 is the condensation process, where the heat exchange takes place and the heat rejection takes place. It reaches to state 6, which is a saturated liquid, but while during the expansion it again have some flash gas as well. This flash gas is removed in flash tank, as we have already discussed in previous lecture. The flash gas after removal is fed to the point 4, and the liquid refrigerant after separation is now at state 8. This liquid refrigerant is now fed to the throttling valve, where expansion takes place, and now it reaches to state 9. Then we can clearly see from here that the quality of vapor has reduced, which was initially coming at zero point 0.7, now it is coming at 0.9 because of the combination of flash tank as well as the liquid intercooling. So here we can clearly see that the refrigeration effect increases if we will have a combination of both flash gas removal as well as the intercooling. The present slide shows the advantages of the combined system, which shows that quality of the refrigerant entering the evaporator reduces. When the quality of the refrigerant entering the evaporator will reduce, it will have an increase in the refrigeration effect. It will lower the pressure drop and as well as the better heat transfer rate. Second point is reduction in the throttling losses, because the vapor produced during the throttling is now separated and only the liquid portion is now fed to the throttling valve. So there is always a reduction in the throttling losses. Third point is volumetric efficiency of the compressor increases, because there is a reduction in the compressor pressure ratio, because now we are compressing it in a two-stage compression process rather than compressing it in a single stage compression process. Also, we have the formula volumetric efficiency of the compressor is equal to 1 plus C minus C P2 by P1 के power to the power 1 by n, which shows that minus C P2 by P1. Now P2 by P1 portion is lesser because we are compressing it in a two-stage compression. Hence that negative portion has now been decreased, hence the volumetric efficiency of the compressor will be increased. Fourth one is the compressor discharge temperature reduces, because now we have lesser compressor discharge temperature, so we will have a better life, and also it will not be lubrication portion will also be better.